Is time dilation real? Physics explained. Imagine you're on a spaceship traveling close to the speed of light. Would time feel the same for you as it does for someone standing still on Earth? The answer is no, and that's because of a strange but real effect called time dilation. It's a concept from Einstein's theory of relativity that shows time doesn't always pass at the same rate everywhere. Instead, it depends on how fast you're moving or how close you are to a massive object like a black hole. Time dilation happens because the speed of light is the same for everyone, no matter how fast they're moving. When you move really fast, close to the speed of light, your clock actually ticks more slowly compared to a clock that's stationary. Think of a clock made of light bouncing between two mirrors. If you're moving, the light takes a longer angled path, so it takes more time for the light to bounce back and forth. To an outside observer, it looks like your clock is ticking slower. There are two main types of time dilation. The first is caused by speed, called special relativity time dilation. When an object moves near the speed of light, time for that object slows down compared to someone at rest. This has been proven in experiments with tiny particles called muons. These particles are created high in the atmosphere and travel at speeds close to light. Normally, they should decay quickly, but because they're moving so fast, they live longer and reach the Earth's surface. This is a clear sign that time slows down for objects moving at high speeds. The second type is caused by gravity, called general relativity time dilation. Near very massive objects like black holes, gravity pulls on time itself, making it run slower. Even on Earth, clocks at higher altitudes tick slightly faster than those at sea level because gravity is weaker up high. Scientists have tested this by flying atomic clocks on airplanes and comparing them to clocks on the ground. The moving clocks showed tiny but measurable differences, exactly as Einstein predicted. Cosmic ray muons provide another proof. These particles are created in the upper atmosphere and travel at near light speeds. Without time dilation, they wouldn't last long enough to reach the Earth's surface. But because their internal clocks slow down, they survive longer than expected, allowing scientists to see the effects in action. Interestingly, because Earth spins, the top of your head is actually aging a tiny bit faster than your feet. This is because gravitational time dilation slightly outweighs the velocity effect in that area. So, technically, your head is a little older than your toes. In everyday life, the effects are tiny but real. For example, if you fly across the country at high speed, your clock will be slightly behind compared to someone who stays on the ground. This isn't just theory. It's a measurable, proven phenomenon. Time dilation shows us that time isn't absolute but flexible, depending on how fast you're moving or how close you are to a massive object. It's one of the universe's oddities that makes physics so fascinating.